I'm really excited to be here, as much as I am delighted, in fact. And so Jonathan recommended that I do my best to steer a little bit of discussion and debate around the issue of reproducibility. And so I thought that an interesting way to kick off the discussion, if you like, would be to mention what has been possibly one of my most debated papers, which is really an opinion piece that I see was sort of lifting doubts on the idea, very common and commonly expressed today as well, that there is a reproducibility crisis. And it's been, is there a laser pointer here? No, I guess not. So is that the red one? This is going to go back. Oh, thank you. Perfect. Sorry about that. Yes. So you can see how even online it was rather remarkably debated. It's been tweeted about over 270 times, and it still is being tweeted. So for example, recently, as a comment to a completely unrelated paper that I published on bioRxiv with, as it happens, David Moore, who's here as well, this is what someone had to say about it. I was impressed by the profundity of the debate. Fanelli can go and stick his head into a donkey's bottom after that turd, and of course the turd is the pianist play. So the point here is that people apparently feel very strongly, at least some people feel very strongly that there is a reproducibility crisis, and I hope you're not as passionate and a little more willing to engage scientifically with the idea. But clearly, fair enough, a lot of people clearly are still on board with this idea, and yet we're all looking at the same data. So these are, of course, not all the studies, but certainly the most prominent studies that have tried to measure reproducibility. And most of them, as you can see, indicated a reproducibility rate, if this counts as a rate, which is something that we will be discussing, but above 50%. And the thing is, to me, even this initial rather, in the eyes of many, grim sort of suggestion of a 36% reproducibility rate was actually, from my light, rather not bad at all. Certainly better than what could have been the case, given everything that I was thinking at the time could actually be going on in, especially messy fields, no offense, like psychology. I meant that I didn't mean to offend anyone. But so there's a logic to the messiness that I'll describe. And indeed, to me, it was always obvious, and it became sort of increasingly obvious over time, that reproducibility shouldn't actually be expected to be 100% in most situations. And in my view, right from the start, what these increasingly impressively sophisticated studies that meta-scientists have conducted over the years have not quite settled the matter around crisis or even around sort of the whole issue of reproducibility. Rather, they uncovered a series of rather deep and fascinating to me methodological and theoretical challenges that the whole idea has. On a rather superficial level, we have not quite established how we should measure reproducibility. And we saw examples today that what we typically try to do then is use different criteria. And the truth is that behind any of these criteria, there are choices that we are making, there are hidden assumptions that we are making, and so on. At a deeper level, we often seem to be unclear or conflicted about what exactly we are doing this for, what it is that we're trying to measure. Because, setting aside all the publication biases, the p-hacking, and all these questionable practices that we know and love, there are plenty of reasons, some of which were mentioned right before this talk, of factors that we understand sort of somewhat would interfere with this idea of reproducibility. So, and famously in debates that I'm sure you're all familiar with, people have talked about the contextual sensitivity of, for example, social psychology phenomena in particular, and others that probably will talk about it later in this conference have pointed out how we understand very well the existence of reaction norms in biology. Or, on the other hand, it's also well understood that methods somehow are likely to change because we don't know everything about even what ourselves are doing. All, in fact, in most reproducibility studies, are to some extent changed willingly, because we need to sort of make some obvious changes in order even to hope that the effect will replicate. And at an even deeper level still, I think there's an interesting realization of how papers can be read at different levels. And one level is certainly that of the finding itself, in which case we would presumably expect it to, or hope it, wish it to replicate simply by applying the same exact methods on different populations, on new samples, and we should sort of observe it working every time. But on the other hand, behind a paper, typically there is a theory, there is an idea, there's a concept, and success in that case would look like this concept working, giving us the right insights and predictions or explanations along different kinds of phenomena, different kinds of dimensions, different outcomes, completely different methods, and so on. And I think what this, at the end of the day, tells me is that the field of metascience is still in what Thomas Kuhn would have described as a pre-paradigmatic stage. Or rather, maybe there is a paradigm that is currently sort of bringing us together, which is the one that there is a scientific crisis and there are all these issues with research methods that we need to address. But as I articulated before, I think it's actually a wrong paradigm. And so what this amounts to is that, in my view, we are lacking a genuinely meta-scientific theory and methodology. And the fact that we don't have it forces us to make some generalizations or simplifications at times that can be improper or confusing. So what I think generally happens to all of us is that we all are sort of born into a certain field, and we only really know our own subject matter. We have experience with sort of a certain kind of research, a certain types of problems. We are experts in certain methodologies. And then sort of inevitably we project that kind of experience to the rest of science. And so we'll make these grand proclaims about what science sort of is in trouble for, or what is happening there. And similarly, technically we have statistics as a reasonably general and abstract language, but again, in the kind of statistical methods that we use, which were typically developed in specific fields in response to specific needs, there are hidden assumptions that we are often forgetting about, or in any case, are sort of a source of trouble for our analyses. And we have philosophy of science often. In fact, I think Popper was already mentioned at least once today, which certainly gives us a sort of an abstract ideal of what different kinds of healthy or unhealthy sciences would look like. But that, of course, doesn't quite give us a scientifically approach to understanding and measuring and studying these problems. Okay? And of course, I'm oversimplifying things a lot. But I genuinely think that even some of the issues that were emerged in the talks today sort of reflect this state of affairs still. At any rate, this is my soapbox. Okay, so this is where I'm going to climb on top to then make my grand proclaim, which is, of course, that I'm going to offer a solution, at least, in what I'm going to call Ktheory, which is a theory and methodology that I claim, out of a sort of a rather reasonably simple approach, answers several core meta-scientific questions. So what I hope and I intend to do in the next 21 minutes remaining is to briefly introduce Ktheory and then effectively showcase various aspects of how I think Ktheory could help, for example, in our understanding and studying and measuring and testing reproducibility. And indeed, I'm going to show how the theory itself is sort of testable, for example, in terms of reproducibility. Of course, you're warmly welcome to download this open access paper, and it is admittedly a rather long essay, but it's very modular, so you can pick and choose the sort of topics that might be of interest to you, and you'll find the directly concrete examples of how sort of the methods work in that case, and the sort of insights they might propose. So fundamentally, Ktheory starts with the idea that knowledge, it's always the same phenomenon ultimately, no matter how it's realized in practice, and it's a matter of information compression, which therefore means that effectively knowledge is, as you read, a system-specific property, which is quantified by this basic, rather simple function, which I'm going to call the K function, And the quantity it gives, I'll just call K. And it's a function that, as you see, is based on information. So these H functions are Shannon's entropy that you see here. And generally speaking, any negative log of a probability is a measure of information. If you're not quite familiar with the concept of information, and it's quite unfortunate that most of us, including myself, don't really get trained right from the start in information theory, and I think it would make a significant change. You can think of a sort of a game that at least some of us, the slightly older of us, including myself as kids, played, which is the 20 questions game. If you play your cards right and ask binary questions that are sort of equiprobable, you are surprisingly effective in guessing what someone is thinking. A binary question, particularly if it's equiprobable, is giving us 1 bit. And these logarithms are all going to be logarithms base 2, because everything I'm going to talk about we measure in bits. So what the K function is telling us is essentially that knowledge is always about compressing some information that is contained in an explanandum, in some phenomenon we want to have information about. And we do this through an explanans that very typically, although not necessarily, consists in an input, which you can think about as the sort of intervention in an experiment, or even better, the kind of independent variables that you would measure in some observational study on a regression analysis. And what instead will always be there implicitly or explicitly is a theory or a methodology component, which is some structure or a list of conditions that essentially defines the conditions under which the pattern will be observed. Okay, so this in the most abstract terms that I could figure is what knowledge is. By the way, so compression is typically lossy, except in mathematics. And so typically what we're also confronting, of course, is some level of imprecision. So it's a residual sort of entropy here, which we might call our residual ignorance. So fundamentally, okay, the equation that I just showed you is derived theoretically. It's derived from a certain understanding, a certain assumption of what knowledge is. So sort of it's the translation of simply a concept of what knowledge is. But interestingly, this translation then turns out, for example, to be transformable in the ordinary measures of effect sizes we all use. So here you have the R squared, Cohen's d, or chi squared as example. I didn't try them all, but at this point the conjecture is that fundamentally anything that we consider a measure of effect is structured in a way that is captured in part by the K function. Although you'll see how for any given value of an effect, size of a classic effect size, you can have different values of K depending on other factors that are in the K function that ordinary measures of effect size don't quite compute. And the other remarkable aspect, which I'll only mention briefly, but again, there's more in the paper if you're interested, is that unlike ordinary measures of effect size, this K function has a physical interpretation. How many of you are familiar with Maxwell's demon paradox? Okay, well, that's a few, but maybe it would require some explanation. And this is a particular version of the paradox. So the paradox would be about an ideal demon, so some sort of entity that operates, that just by manipulating molecules, for example, separating hot and cold molecules, or in this case, just knowing where a molecule is effectively, could, it seems, extract work from a system or create order in a system without creating any entropy, and therefore infringe on the laws of thermodynamics. And this particular version of the paradox is the one that solved the paradox, at least in sort of it's now, let's say, generally agreed in physics that this is a solution. And it comes from the fact that information is now understood to be a physical quantity. So the solution comes from the fact that in reality, whatever the version of the paradox you like, the demon needs to measure something about the molecules and therefore needs to store this information in memory. And then we'll have to erase that memory. And the erasure of memory, or the erasure of information effectively, even in computers, it's now understood to be where this entropy gets released, sort of saving, okay, the second law of thermodynamics. Point here is that each of the terms that would define a system such as this one has a corresponding value in the K function. And so, as it turns out, the K function is, in a sense, a measure of efficiency of this daemon. It tells us what good a job an entity such as this one would do in transforming the information it can gather into order or work. Coming a little closer to the issue at hand, the fundamental claim of the theory itself is that this measure K, or sort of slight variants of the same idea, plus this lambda that we'll see in a second, are fundamentally what allows us to measure knowledge in different contexts or track knowledge over time within a field or a discipline and so on. In particular, we'll use a little bit this predictive K, which is exactly like the K we saw before, except that it has a cross entropy here rather than a simple entropy, which means concretely that this quantity can now be negative, the way that the sort of ordinary K here wouldn't. And without going into detail, part of the point that I made before, and I'm picking up back here, is that those challenges that people understand or sort of confronting us when we discuss and study reproducibility represent terms that somewhere are in the K function or quantified by it and have effects on K. And so one of the remarkable aspects of this approach is that in a single number, or to be fair, sort of in different versions of the same idea, let's say, but one has a whole range of values that is capturing, in a sense, if anything, by the limiting values that these quantities would approach asymptotically, the different conditions that we might be interested in. So we go from plus infinity for a way that I'll show you later on to actually count the number of bits of knowledge that we get about some phenomenon, to a limiting value of 1 for the theory that sort of works beautifully across all sorts of different tests, to a limiting value that is lower, typically 1/2 or lower, for instead a single finding, okay, the typical object of a reproducibility study, the way we currently do them. And of course, when K is 0, that means that the finding, the theory, or whatever we're looking at is flawed. It doesn't predict above chance. But interestingly, particularly if we then talk about the K predictive, when the theory is wrong and is systematically making the wrong predictions, then we have a negative K, as if to say we're losing knowledge instead of gaining it. And interestingly, and this sort of can be shown mathematically, analytically, that if instead of changing your theory, you're sort of saving the theory by changing your methods, post hoc or with ante hoc biases in study design, essentially, you're entering the realm of the pseudoscience, which is as negative as it can get. It could be technically infinitely negative in the amount of knowledge it gives. So in practice, this is, for example, how a K analysis of registered replication reports would work. This is a particularly interesting case because it has 5 different outcomes that, at least for the purposes of illustration, I'm going to consider as 5 different dimensions. So the blue is the original finding, here reported as K predictive, so weirdly enough, but it's different from the actual K of the study. Then you have all the sort of registered replication reports in decreasing order of magnitude, and then the red bars are the aggregated value for K for the entire data set, which you then see reported here again. And the green bar is the multidimensional K. So the green bar is what now it's aggregating all of this data set, taking into account the fact that this is 5 different dimensions. So just to illustrate what it means to have multiple dimensions, you can pick out how here these red bars are kind of an average of what's going on. It's not exactly an average, it works a little differently. But essentially, it's not surprising to see this height for these red bars, whereas the green bar is actually surprisingly high. It's not quite an average of what you see here. And that's because, apart from considering how positive the overall predictive knowledge is, it's taken into account the fact that these were independent tests. So this would be valued more than not if these were the exact same study. And as I mentioned before, one can, for example, do fun things such as calculate the number of bits that this theory, whatever it is, I don't even remember, to be honest, gives us, because we simply multiply the bits in the explanandum, in this case, including the dimensions, or in fact, this is the same, it's just 5 for the 5 dimensions, by the K that we have, and we get this value of 0.025, which again is sort of the efficiency. And just by comparison, in the paper you find an analysis of psychological differences between genders, and that yields about 1/4 of a bit. So this would be, according to this analysis, but it's sort of a proof of concept more than a real analysis, but 10 times lower. And we can keep aggregating at higher levels. So here you see the same thing for seven, let's say, registered replication reports. And there is a parametric version of it where we assume normality, and so it's sort of nastier, sort of stricter about how good these effects are. And there's a non-parametric estimation, which simply looks at whether the direction is the same, which is more generous with these values. But you see how the results overall are consistent in who's positive and who's negative. And the sort of overall conclusion, which at this point is the K of these entire 7 studies and multiple data sets. So this is one possible use of K, well, the fundamental sort of idea behind using K. But then interestingly, for example, in this case as in others, this theory makes specific predictions about what reproducibility should look like and how we should understand it. And fundamentally, this starts from the idea of what knowledge is in this approach, which is a relatively improbable structure encoding a signal. Okay, so in other words, unlike the kind of assumptions we typically make, and again, sort of simplifying a little bit, but we typically make, for example, in meta-analyses, we're not assuming that the original study is just a random draw from a population, that is sampling some true effect that underlies it, but is effectively the result of a search and optimization process, partially along the lines that were discussed this morning. And it's a process that extends over time, and it's not just about that paper. It probably goes back to what built certain beliefs and certain expertise and certain knowledge in the scientists, as well as, interestingly, for example, it's probably not independent of where it is discovered, for example. No? Because by definition, conditions that make that effect more probable, make the discovery of that effect more probable. So in short, any reported effect is bound effectively to have condition factors that we don't know completely. Even the researchers that report that finding are probably unaware of them, not to mention the fact that many of these factors will not be communicated completely. And of course, entropy is going to creep in. And so, long story short, we can show that sort of on the average, this is what the relation between the K of a replication study and the K of an original study should look like, okay? Where this is the dot product of 2 vectors. Essentially, it's a series of divergences between the 2 systems multiplied by some loading about how impactful that divergence is. Fundamentally, this is the kind of curve we're talking about. It's a negative exponential curve that, depending on how large these lambdas are, is going to approach 0 more or less rapidly. And very quickly, because of course I'm already pretty late on schedule, but it's worth mentioning that the kind of assumptions that we're often looking at are just simply special case of this picture. So for example, assuming that there's a symmetric random distribution around the original effect is in our case simply saying that the divergence is 0 or approximately 0. Or interestingly, for example, p-hacking, in a sense, we can understand in this context as just another methodology, that it's simply producing a very large explanatory K for a sample, for a particular event, but is not going to produce an equally large predictive K. And similarly, in this vision, there are no true or false effects, because any effect is simply system-specific. But notice that with other methods that I'm not showing here, we can actually quantify the costs of these post-hoc biases, and that's where, for example, being a pseudoscience comes in. And similarly, reproducibility is not a binary state, and that's been presented in such a way, for example, today several times. Now, in reality, in this vision, it's simply sort of a continuous factor that is relative to divergences between the 2 systems. And by the way, as I'll illustrate in a second, therefore, we typically will not predict it to be 100%. How do we test these ideas? Well, we very simply transform this function into a linear model just by taking the log of the ratio between the 2, and so now we have something that we can estimate by maximum likelihood. And we have very specific predictions to make. So we predict this ratio, in a sense, all else equal to be constant, or in other words, there's a proportionality between original finding and replication finding. The lambdas, and this is a rather strict prediction if you think about it, are, at least on the average, let's say, going to be smaller than 0. So we predict all these effects. Now I've sort of removed the minus from here. But we expect the lambdas to be negative. And of course, we expect the reproducibility to work, to be inversely proportional to the divergences. So this is what, for example, sort of like that kind of analysis would look like. These are results from the reproducibility initiative in psychology, cognitive psychology and social psychology data. Here you have the estimated lambdas, and you see they are both negative. And here is how, essentially delogging, we get what is effectively sort of kind of a proportion of success, but notice how this is calculated in a completely different way. Now, we also mentioned that we have other predictions, such as this ratio should be constant, which is what we're assuming to be the case by, so this would be the identity line, the dotted line, whereas this is our new line, which is simply sort of parallel to the identity line, but it's lower, has a different intercept. But notice how, particularly in cognitive psychology, the linearity of the relation is actually quite remarkable. And except, for a little bit of noise at the lowest levels of K. Social psychology, as in fact was pointed out already in the original study, now I'm not saying anything new here, sort of looked not too bad at the beginning, but clearly there's more going on here than there is in cognitive psychology. And we can, of course, do all sorts of tests, for example, compare the two and conclude that indeed the lambda of social psychology is lower than that, sorry, it's larger than that of cognitive psychology. Or in other words, it's less reproducible. And so, for example, this lambda, as I hinted at before, is, in my view, the measure of reproducibility that we should use. And it would have a few advantages. Here I'm comparing the RIP with Kammerer's 2 studies on experimental economics and social scientific experiments in nature and science. Lambdas, again, are all negative. But interestingly, this lambda, if you think about it, first of all, it's a quantity that it technically could have any value, although we predict it to be negative. And it's a scale-free metric, okay, because it's derived by this process that is, again, sort of it's detached from any sort of measurement or scale. And just by converting any study into Ks, we can extract it from any study with no added criteria. We don't need to think about p-values, confidence intervals, none of that. And we can do fun things with it. This doesn't really apply to this case, but for example, if the divergence was in time, we can measure something as crazy as the total knowledge that that particular theory could ever possibly give us by just integrating the function, and we get this nice sort of simple formula, which tells us, for example, that the lambda has this interpretation in terms of a half-life of knowledge. And just if you're curious about these results, it would turn out that experimental economics and cognitive science are pretty much the same. This is a slightly larger, but not, I wouldn't say, not remarkably in any way. And both are more reproducible than social scientific experiments, which are more reproducible than social psychology. And but this is just the beginning of the story. Of course, what we might be interested in doing at this point is explore what are the sources of these lower reproducibilities, what divergences are most important in the systems. And just as an example here, what I did was to test for 3 possible factors that were very objective to measure, which is the difference in mean between the controls of original study and replication, standardized, a binary variable separating replication studies done in different countries from the original, and a similar one about the population, which is in this case is essentially whether the population of students was sort of the same, typically psychology students, rather than a broader population of students. And I did this on only the RRRs that had at least 5 data points for each of these factors to make the assessment robust. And you see that this is a random effects model. So I'm allowing these lambdas to vary randomly across the data sets in the attempt to make them more generalizable. And again, notice, by the way, how all 3 are negative. And this is sort of the delogged plot of some of these curves, how they would look like. But the fun thing is that since these loadings are now sort of arguably, let's say, generalizable, we can use them now to predict, let's say, forecast at least what's going to happen in any reproducibility study. So here I do this back, taking all the data from those 7 registered replication reports. And so this is what our ability to predict sort of the ratio looks like. And it's a tiny effect. Okay, we're explaining about 5% of the variance, which is not huge, but it's not bad if you think about how coarse-grained this analysis was. But of course, notice that our original sort of theory tells us that the original value of k is one important predictor of the k of the reproducibility study. And indeed, if we add this factor, our explained variance goes up quite a bit. So it all fits essentially with the kind of theory we outlined before and the kind of predictions we made. And similarly, a little more daringly, just again, as I emphasized, as a proof of concept, but I took the data from the reproducibility initiative in psychology, and there was at least one factor that very easily I could sort of derive from the data. And so just by adding that factor to our predictions, we get a fit that, at least based on residuals, sums of squares, is, you will agree, much nicer. It starts to look like the kind of cloud of points that we wished we could have had. This would be our hard prediction. So there you have it. And I know that this is not a modest proposal, and I'm not a modest person, but I'm doing my best to look humble. And in any case, it's a sincere proposal in the sense that I've been thinking about these matters for a long time, and seeing them in this way has changed my views on many matters and has helped me understand, from my light at least, I presume, these problems more clearly. Again, these were just proof of concepts, and the data itself has a number of limitations. Interestingly, these are not experimental studies, and as we mentioned before, they're bound to have been modified a little bit. For example, when we change country, typically we have to translate all the texts. So those adjustments actually are against our hypothesis, they're against our prediction. So what you saw are effectively rather conservative estimates of the impact of those divergences. Finally, as I mentioned, reproducibility itself is just one of the possible topics in metascience that I think this approach can help address in a truly meta-scientific way. And I can only hope that I succeeded in capturing your curiosity enough that you will want to have a think perhaps as to how these methods could be used on your data. And of course, I'll be happy to discuss this matter. And I'm looking forward to insightful and sort of placate and calm comments and suggestions. Thank you very much.
Thank you. It was a great talk, and I have a question. I'm Boris Weitzman. I'm from Chan Zuckerberg Initiative. In machine learning, there is a thing called overfitting, when you can describe what you saw, but you cannot predict what new data. When I look at your p-hacking equations and some other equations, I see really strange similarity to what they do in the theory of overfitting. So my question is there a parallel, and can you use really good mathematical apparatus of prediction theory in machine learning and try to put it in, try to merge it with your K-theory?
So I don't know specifically about, I didn't know that a sort of an overfitting theory existed in machine learning, but I'm not surprised. I'm well aware of the problems. And I think a lot of people in meta research sort of are aware of the problem in that terms anyway. Data mining has been going on for a long time in plenty of fields. And I'll certainly look into it. So that's a great suggestion. The other thing to point out is that the parallel wouldn't surprise me at all, because indeed, in a sense, what we're arguing here is that it's always the same process. We're all, in a sense, sort of, as in fact was mentioned by other talks today, that's what we're really engaged in is a computational process. We're compressing somehow the information. And so when we do it with machines, it's ultimately not different.
Absolutely. Same.
Hi, thank you so much. That was inspiring and exciting. So when you framed the whole problem you asked, what are we trying to reproduce? Are we trying to reproduce the effect or the theory underlying the effect? And I understand how in an information theoretic framework, you can sort of look at the prediction versus the signal and see how well they match. But if you're really thinking about that sort of underlying theory, right, as the theory morphs toward something that's more true or more predictive, that error may behave chaotically as your underlying theory gets legitimately better. So is this sort of difference, this like fundamental difference between statistical error and epistemological error, something that can be addressed in K-theory, or is that to do with how you interpret results from K-theory?
I'm not sure I understood the discrepancy that you're pointing out.
If I have a theory about something, and my theory is getting better, I may, if the sort of underlying abstractions that I'm thinking about do legitimately get better, that.
What do you mean by getting better?
Yeah, get closer to some sense of ground truth. As your abstractions that you're working with change, your predictions can vary sort of wildly, right? You could take a bad theory and sort of overfit and get something that's close to what you're trying to predict with the very wrong abstractions. Or I guess, to not take up too much time, is the concept that there is a difference between statistical versus epistemological uncertainty something that is addressed
Statistical and epistemological uncertainty.
Yeah.
So certainly my attempt is to get to the latter, which is really what we should be interested in. Perhaps if this addresses your doubt, there are different ways to sort of define the problem of measurement of what counts as sort of successful predictions. We could be very strict and say that the theory is predicting those values, as it probably very often happens in physics, and therefore any deviation from that shows that there's something wrong, or one can be more cross-grain to different levels. And that is something that we define. That, in a sense, is part of what it means that knowledge is system-specific. Yep. What we want to study, maybe in whatever meta-scientific problem we define, it comes in part from defining the system itself. And so the two have to go together, and they're not separable. Perhaps that.
Okay.
I did my best, but maybe we can talk more later.
Okay, it's me now. Hi, Paul Smaldino, UC Merced. Yeah, I have a lot of feelings about this talk.
Great. Let's hear a few of them.
So I do have some training in information theory, although it's been a while. And I totally agree that information theory seems like a really good approach for trying to understand whether or not something is reproducible. I didn't fully understand K and how it works. I mean, that seems like okay in a span of this time, but I wonder to what extent you can. I guess my most pressing question is, to what extent could this be married with or translated to the very, very rich amount of theory that already exists in information theory with measures like KL divergence or mutual information?
Oh, so the K function is a standardization of the mutual information. It follows entirely from not just classic information theory, but algorithmic information theory.
Right.
I think that's part of the history of why maybe this kind of thinking hasn't emerged before, although, I didn't sort of construct all this. A lot of what this is about, in a sense, is condensing in a sensible, simple approach ideas that have circulated in sort of various contexts for years. And that's, in fact, something that I discuss in the paper as well. That,
right.
Rest assured that sort of we're not ignoring all that theory. Quite to the contrary, I think part of the operation here is truly taking stock to the full of those kind of insights.
Okay, so really quick follow-up then. So, I mean, to get measures like that, you need not just a single study, right? You need a whole bunch of things to sort of average over and get a distribution. So this seems like a way to estimate, like as you sort of pointed out, the reproducibility of a field or a subfield or a body of work. So I don't. Can you clarify how you're getting the individual data points and how you could use this, if at all, to measure the reproducibility of a single study?
Right. So yeah. Ideally, there are, as you know, a couple of ways. So the most fundamental way that I, as much as possible, would like to see done, and I do it in the paper as well, is so-called maximum likelihood, but essentially it's sort of the empirical probability as measured. You know, you discretize whatever measures you have, and out of that probability distribution, you derive the entropy, for example, for that particular variable. That becomes impossible effectively very rapidly when one considers multiple dimensions, and so one has to introduce modeling approaches effectively that will derive from empirical distributions what is the likely underlying probability distribution and derive entropy from there. The third way that one can do it, it doesn't satisfy me at all, but sometimes it's necessary, is instead directly analytical. So as you know, for practically all the common probability distribution, there is a formula for entropy. And so technically, once you have, in fact, in the case of the Gaussian, for example, you just need to know the variance to derive the entropy from it. Now, again, I don't like that at all, because I think part of the problem is that with all these assumptions that we're imposing on the data when we analyze it. But in general, again, there are different approaches. And that's actually one of the the anticipated criticisms that I addressed in the paper. So in the discussion section, I answer maybe a little more completely. But the point is that now we have powerful computers. This is also why we can play around with entropy as much as we couldn't do before. And the other is that there are, for example, increasingly sophisticated analytical approaches to measuring the entropy of mixed distribution, which is a pretty complex thing to do. Again, kind of stuff that, that wasn't possible in the past, but by now would make these methods implementable in real data with not too many technical complications. Maybe that was too long, sorry.
Hi, I'm Bobby Spellman, University of Virginia, retired editor of Perspectives on Psychological Science. I have a very different kind of question for you. So in the past, I've really loved your research, but
there you go. There's always
the PNAS paper pissed me off no end. And let's just start with the title, okay? So the thing that really bothered me about that title is you used the phrase reproducibility crisis. And I wish we would stop using that phrase.
I agree.
If you want to use a phrase like Renaissance, like your chair of the session here does, or revolution, like I used to do, or reformation, like Danny Kahneman and I did, I think that's so much better. And the reason, I think, is because I think the crisis phase is over. Like, I think a crisis is a thing when, oh my God, Ebola comes and you don't know what it is and you don't know what caused it and you don't know how to respond to it and you don't know how many resources it's going to take or anything like that. And I think now, due to a lot of the work of the people in this room, we have a good handle on how big it is, on what the causes might be, and really about ways to address it. So I think there's like 4 people in this room who never believed there was a reproducibility crisis, and 396 people who are trying to do something about it. So please change the language.
But I don't understand. Are you saying that there is no crisis? Because essentially I would agree with everything you said. So I wonder why you hated the paper so much. Did you just read? Did you just read the tweet?
No, I tweeted about it. Yeah. No, it's really the title I hated about it. That just let's not even use it anymore.
So, but that's my point. But you know, and besides, it's not even a political argument. I'm saying the evidence doesn't back it up. We didn't have evidence before, and it was fair enough to be concerned. I thought that, again, things were sort of going to look terrible. Now we have the data, and the story has to change, in my opinion. Okay. I totally agree.